To continue from our last class, we were discussing lambda functions and lambda expressions in Java. Java is an object-oriented programming language. However, it's not immune to the need for functional constructs. That's exactly what we were looking at. Onward to learning more about lambda expressions. We've just learned that lambda expressions are basically function objects, anonymous ways to define a single function and treat that function as an object. Now, lambda functions are especially powerful when the output of one lambda functions is kind of fed as the input into the next. Think of this as a chain where the input comes in, you apply a lambda function to it, receive an output, and feed that output to the next lambda function. Even better than a chain, the better analogy is an assembly line. If you think about all the operations on an assembly line as lambda functions, on the conveyor belt the input comes in, you perform some operation, and you pass that part on to the next person in the assembly line who performs another operation. Now, Java has added exactly this functionality as a part of its programming constructs, using something called aggregate operations. Aggregate operations are basically every function in an assembly line: filter, map, and for each. These are standard aggregate operations which are used in functional programming. So these basically form the various functions that can be done as a part of this assembly line: filter, map, and for each. Java provides a very simple way to use these standard functional programming aspects to collections like lists, maps, sets, and so on and so forth. So not only do these aggregate operations exist in Java, Java also makes it very easy to use them. And in fact, collections are typically where we apply lambda functions because that is the conveyor belt. We'll see how easy it is to use these aggregate operations on collections. The Java collections interface offers a method called stream. You can simply call the .stream method on any collection to get an object of type stream, and it is this object on which aggregate operations can be applied in sequence. So what is a stream? The easiest way is to go back to our original analogy of the conveyor belt. The .stream method will basically convert this collection to kind of a conveyor belt format which streams down. Aggregate operations are basically the different stations at the conveyor belt, and they can be applied on the stream. The Java stream object can also be imagined as a stream of values where each value is being subjected to an operation. What are these operations that can be applied to a stream? Map, for each, and filter. These are the most standard operations which are applied to a stream of objects. Let's take a look at the very first aggregate operation, which is map. This takes a lambda expression and applies it to every element of the input stream, and as the results come out, it's sent out to the output stream. So map is an operation. Map has a lambda operation which is applied to every element in the input stream. It changes that element in a certain way and sends those changed elements out in the output stream. Visualizing this will make it much easier. So say we have an input stream x1, x2, and x3. These are the various elements which are coming in as a part of the input stream. We have the aggregate operation, and in this case our aggregate operation is the map. Say the map has a lambda expression, let's call it f of x. F of x transforms every x that comes in as a part of the input stream in some way, such that the output is f of x. This changed object is sent out to the output stream. So for x1, x2, x3, we'll get at the output f of x1, f of x2 and f of x3. Two things to note here. One is the map applies to every object in the input stream. And the second is the map changes those objects in a certain way and sends the changed objects to the output. Let's now look at what filter does. Filter is also an aggregate operation which takes a lambda expression that encapsulates a condition. So the lambda expression associated with the filter operation is always a condition which evaluates to either true or false. It applies this condition to every element of the input stream. Every element which returns true, which means it satisfies the condition, is placed in the output stream. Again, this is far better understood diagrammatically. So say we have an input stream x1, x2 and x3, and we have the aggregate operation that's going to be applied to it, which is the filter. A filter is basically has a lambda expression which has a condition within it. So the f of x associated with a filter aggregate operation is usually of the type if condition then true, else false. Now, this condition can be applied to every element that comes in the input stream. The elements are filtered, that is, only those which satisfy the condition move over to the output stream. The rest are simply, you can imagine them as being swallowed by the filter operation. There is an easy analogy for the filter, and that is quality control on an assembly line. So you can imagine all these parts come through, and when the filter operation is applied, quality control is done. We check for bad parts, they don't satisfy the condition, and we simply remove them from the conveyor belt. The good parts go through. So in the example that you can see on screen, x1, x2, x3 came in, and basically we realized that one of it doesn't meet our condition. So only x1 and x3 are present in the output stream. Let's take a look at the last standard aggregate operation, which is the for each. For each also takes in a lambda expression and applies it to every element of the input stream. It works exactly like the map. However, the important difference is that it does not produce any output stream. So for each simply swallows all the elements, and it is usually the terminating lambda expression in this entire conveyor belt of streams of objects. So say we have the input stream x1, x2, x3, exactly like we did before. And the aggregate operation that we want to apply here is the for each. Remember that the for each is applied as a terminating operation. So it's usually the end result after the objects have undergone all the transformations and the filtering. So you'd usually have an f of x, something like print this element to display, or output it to a file, or send it over the internet. This is a terminating operation. There is no output stream. So for each is typically used for operations like printing to screen, saving to file. All of these cases, it makes no sense to produce an output stream. Lambda functions or lambda expressions are excellent examples of the command pattern in action. And hopefully this makes your understanding of the command pattern even clearer.